Okay. So yep, we're gonna get to, we'll skip, like it said, we're gonna skip over catalysts and get to the assignment slide. So, reaction mechanisms. Hi. Reaction mechanisms. I've been kind of alluding to this, and when I like stand up here and we see a chemical reaction, but when I kind of go like this, behind the scenes, that's actually my list of elementary steps behind the scenes that are happening behind the scenes. That is actually what we call the reaction mechanism. Okay. And these kind of lists, and actually I was getting ready for today's lecture, and I thought, well, that's like Hess's law. Because honestly, one of the things we know about Hess's law is you can take these little baby steps and add them together to get the overall reaction of interest, and that's actually what we're going to do with our reaction mechanisms. Notice, though, that the things behind the scenes, the little baby steps, actually those have to be literally what happens with the chemical reaction, molecule by molecule. Okay? So these things I list over here, these are elementary steps. They add up to be the overall reaction of interest. Okay? It's a single step in the mechanism. Add up the elementary steps, and you have the reaction of interest. Okay, so we're going to get some more work at, remember you line up along the reaction arrow and add reactants and add products and let things cancel. So it's like Hess's law. Okay, so again, I'm dealing with elementary steps. So I'm trying to differentiate between the reaction of interest and the elementary steps, okay? So the elementary steps have this thing called molecularity for the elementary steps. The molecularity is the number of particles on the left. It's the number of reactant particles. Right? Not so much, just the left. So molecularity, which is kind of hard to say sometimes. So we have unimolecular. Uni might kind of give it away, one. Okay. Basically, these are great for your decomposition, elementary step, or rearrangement. Okay, where A goes to form B, or A goes to form B and C. Then we have a bimolecular, and these are very popular too. Basically, on the left-hand side, you have two particles that need to collide in your elementary step. It's bimolecular. Termolecular, if you want to add not very common, you can, and I'll kind of try to say why that is. Ter or trimolecular. So here we have three particles, not very likely. And I kind of emphasize that later on in my, I almost said minutes, later on in my notes. So a termolecular elementary step is one, and I'll just go tell you why it's not very likely, that literally you have three particles, and they could be all the same type of particle, but three particles that literally have to find each other and proceed from reactants to products. You're like, I don't think so. Okay, life isn't like that. It's not to say that the overall chemical reaction doesn't have three particles. It's just to say that it actually happens in a series of elementary steps. Two particles do their thing, two particles do their thing, and they add up to the overall reaction of interest. So termolecular elementary steps are not very likely. So unimolecular, a couple of possibilities up there. The first one would be like a rearrangement. The other one would be like a decomposition. Unimolecular, only one particle on the reactant side. Again, we're talking about elementary steps, little baby steps that are part of an overall reaction, okay, that add up, they are steps in an overall mechanism. Bimolecular, we have a couple of options here. You can have two different types of particles that combine. You could have the same type of particle, and so to me, the second and third are saying the same thing. Okay, so basically you can have two particles of A combined as part of an elementary step. That would be bimolecular.
Would that be like the diatomic elements like that?
No.
Okay.
I mean, no. We're independent of species right now, but yeah, I don't think so anyway. And termolecular or trimolecular, this is an example of trimolecular, where you have two B particles finding one A particle and proceeding to form a C particle, okay? And then I go on to say why they're relatively unlikely. And it's kind of like pretty random that in your reaction mixture, you're going to get those three particles to come in close contact with each other. So if you see a trimolecular, okay, it's probably actually not its own elementary step. So what this is saying is instead of happening in just one step, it really probably happens in two steps. And actually these might be kind of what we'd say the elementary steps at the molecular level. Remember I said we're going to be kind of using Hess's law. We're going to be lining up our reaction arrows, adding our reactants and adding our products and letting things cancel, etc. If I were to go ahead and do that with these two, notice that our D's cancel. Do you guys buy that? Our D's cancel. We got one of each. Okay, and then bring down what didn't cancel. So to me, I've got a 2B plus A goes to form C. Okay, which actually is this one up here. So
I was going to ask, is there certain reactions where it's more likely for this to occur than others, or is this just a general rule where it doesn't happen?
General rule where it doesn't happen. In fact, we're going to look at some mechanisms, and if in your mechanism one of your elementary steps is termolecular, unless you're in some sort of advanced class, it's not likely to really happen that way. Yeah, it's a throw out sort of thing. So one thing before I move on, we're going to talk about intermediates. So I love intermediates. I'll put a little, okay. So do you see where actually D is formed here and it's consumed here? It's formed in one elementary step but consumed in another elementary step. It doesn't show up. That actually is what we call an intermediate. Right, and it just so happens that's kind of. All right. So yeah, termolecular, especially for this class, I guess I would say, and I don't know, I have to ask Laura, who's, like I said, just kind of finishing up with her chemical engineering, if the mechanisms, because I know that she had homework like her second, I don't know, a couple years ago, and it was like, oh my gosh, that's what we do in Chem 2. So I'll have to ask her. Anyway, okay. So the rate equation for a chemical reaction cannot be predicted from its stoichiometry. So do you guys remember, actually it seemed like just the other day I put it over here and I said if you have A with the stoichiometric coefficient of A reacting with B with the stoichiometric coefficient of a small b to form C, and we said you can come up with a rate law expression, rate is equal to K times the molar concentration of A raised to its reaction order, and remember we just put an M in there, a variable M, but we found what the M's were, right? Molar concentration of B raised to its reaction order, N, okay? And I said you cannot take this and make it into M, and you cannot take this coefficient and make it into N. I said you cannot not do that. Remember that? Okay. But if somebody has knowledge, and if somebody tells you that what they are writing down is an elementary step, really how it happens on the molecular level, if it's an elementary step, then you can actually use the stoichiometric coefficients of the reactant as the reactant or as their reaction orders. Only if it's an elementary step. This is one of those things don't blame me. Okay, I know we got to the end of talking about rate law expressions, and probably some of you are going to try to use your stoichiometric coefficients as reaction orders. Do not do that unless it's an elementary step. I'll show you what it looks like. You ready? Here we go. It looks like this. I know it says you can use molecularity to come up with the reaction orders. So here we go. Notice the first column. It's an elementary step. If it's an elementary step, then actually we can write the rate law expression for this elementary step using the molecularity of A, which is 1. The reaction order of A is 1. So we can actually come up with a rate law expression. Rate is equal to K times the molar concentration of A raised to its stoichiometric coefficient, which is 1. You can only use it when it's an elementary step. I cannot overemphasize that. Do you guys remember how much, like your homework, you really sweated in your graphs to come up with the reaction orders, the M and N's? Only by observing experimental data can you come up with that for an overall reaction of interest, unless that overall reaction of interest only occurs in one elementary step. And I'll show an example. Hopefully this will kind of make sense. Okay, so if this is an elementary step, this is bimolecular, the stoichiometric coefficient of A is 1, the stoichiometric coefficient of B is 1, then actually we can write the rate law expression using those stoichiometric coefficients as reaction orders. This only works because it's an elementary step. So the rate law expression for this one, bimolecular, then is rate is equal to K times the molar concentration of A raised to the first power times the molar concentration of B raised to the first power. Okay, one more. What if it's another bimolecular, but it's like 2 particles of A come together? Okay, stoichiometric coefficient of A is 2. Actually, the reaction order of A is 2 because it's an elementary step. So the rate law expression for this is rate is equal to K times the mole concentration of A raised to the second power. That is its reaction order because it's an elementary step. Okay? Awesome. Okay. So now this is kind of fun. This always reminds me of if you are a family of 5 or 4 or even a family of 3 trying to get out the door, there's always somebody who's slower than the rest. And that person who's slow actually determines if you're going to be late or not. Okay? So that's kind of, that sort of thought is kind of what we have when I'll go over here again. This is the reaction of interest, okay? Behind the scenes, these are elementary steps, okay? Now, and you might say, well, is this always the way it is? Well, yeah, I guess so. Because all of these elementary steps, and we're going to talk about maybe 2, 3, 4 elementary steps, one of them is slow. The others are just normal or fast. The one that's slow is actually going to be the one that kind of sets what we call the rate for the overall reaction of interest, the slow elementary step.
So can you just ignore the other ones then, and then just focus on
Kind
the
of,
slow one?
kind of. And we are for the first. We are for the first, exactly. We're going to turn our soul, heart, and attention on that slow one, and however, actually we're going to use its molecularity to kind of see, well, then the observed reaction rate must be related to that molecularity. The only catch is, and I'll kind of talk about this, is if there is an intermediate that doesn't show up in the reaction of interest. We kind of have to do some cleaning up, but yes, exactly, totally. Okay, so I kind of have a couple of scenarios here. Okay, so what I've been describing, if we call this A and we call this B, okay, and for A, kind of behind the scenes, let's just make them 3. Okay, so let's make them both 3. 1, 2, 3, add them together, overall reaction of interest. And then for B, 1, 2, 3, overall reaction of interest. And what this says is the first step, let's see, the slowest step is the first. So actually next to blah, 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 you're going to see the word slow. Blah, fast, blah, fast. And just like you said, when we go and this is the reaction of interest down here. When we go to say what this rate is, the thing that's driving this rate is that one. And then this one is, it's kind of like, I know you all experience this if you have family members that are slow. You can be as fast as you want. But if you have somebody that's kind of going a little bit slow, okay, then you're going to have to wait on them. And actually, they are going to determine the rate. Once you get out the door. So in music, sometimes when the conductor tells us something, we like put spectacles next to what the conductor tells us. Okay, so actually, you know, those are the people to watch, you know. Okay. All right. So we'll come back to that rate determining step. And we're going to see how that affects the overall reaction rates. So just a little bit ago, remember D was an intermediate, or a reaction intermediate. It's formed and then later consumed. So we have kind of a couple different possibilities with reaction intermediates. Some of them you can actually snag. You know, it's kind of like they magically appear and you can isolate them if you know what you're doing. Kind of sounds exotic to pull the D as it forms before it's consumed again. And some of them, it's just not practical. So you're like, I know it's formed, but I can't get it. Non-isolatable. Okay. So a reaction intermediate. Okay. So when the rubber hits the road or whatever, what you see as an experimenter, okay, with regard to changing the molar concentration of your reactants, changing the molar concentration of your products, your overall rate law expression for your overall reaction of interest, that needs to add up to what you propose. So what you propose, your overall mechanism of elementary steps, needs to be consistent with what you observe. Okay. And if they don't match, you can't pretend that they do. So it seems a little bit kind of like an oxymoronic sort of thing, but a reaction mechanism can occur in only one elementary step. And it's awesome, because if it does, then you can use, I think I alluded to it, if you know it's one elementary step, you can actually use its molecularity to knock out rate law expression. Okay. Or more than likely, and we'll kind of look at both, it's really a series of elementary steps. Okay, so a single step, as long as somebody tells you that. Okay, so this, and I think I have far too many figures of this. I know there's a lot of slides there, but a lot of the slides are just of this one, just images. Okay, so N2O reacting with NO, right? And this reaction is an elementary reaction. Elementary reaction. So it's a chemical reaction that happens in only one elementary step. Only one single step. So see what I mean? Check this out. Okay, so those are the reactants. This actually, I shouldn't blow this off because this is an important thing. So this actually is, it's not an intermediate, but it's actually what we call kind of in transition between the reactants and the products. I'm going to kind of show you where this is on an energy diagram here in a minute. So we basically have the two reactants kind of connecting together, and then we have the products. Okay. Again, the reactants on top, reaction arrow, the products there. Oh my gosh, there's one more. You're like, really? Okay. The reactants, and this one though kind of shows that transition state. Okay, again, where you kind of have, it's in between reactants and products. And this is products. Okay. One more thing. Actually, I think we looked at this energy diagram before. Okay, so this is going from left to right, and it kind of implies we could go from right back to left again. But we have an energy diagram where these are the reactants, and these are the products. Remember we talked about activation energy. That's that barrier that endothermic and exothermic reactions both have. This happens to be exothermic. And then that transition state where we saw a couple of models, there's the transition state up there. A transition state is at the top of the energy barrier. All right. Well, let's take it up a notch. Okay. So in this one, we are going to have 2 elementary steps. The first one, initial one, is slow, and the second one's fast. So we're going to turn our attention to the slow one. So here we go. So this is, I say a classic, you're like, oh, not a classic. So what they did was they went to the lab and they ran this chemical reaction, and they said, this is what we observe. This is the rate law expression based upon our observations. And actually, you guys have done this. You know, you guys, it's first order with regard to H2, first order with regard to ICL. All right. So let's look at a proposed mechanism. A lot of times, you're given the proposed mechanism, and you have to prove that it matches up with the observed rate law expression. This is kind of what that looks like. Okay, slow step. Already, hopefully you're saying slow step, I can use molecularity. It'd be first order with regard to H2, first order with regard to ICL. Well, that's what they observed. We're done. Well, kind of. Okay, in order to get the overall reaction of interest, actually we have an intermediate, which is HI, reacting with another ICL to form I2 and HCl. If we clean this up, letting things cancel, that can cancel. Looks like we combine terms. We have 2 HCl's. Our HI's cancel. Okay. So the overall reaction of interest looks like this. H2 plus 2 ICl goes to form I2 plus 2 HCl. Again, we have an intermediate. And I don't think there's much more to prove. Okay, maybe I have it on my next slide. But it's just like we were saying. Once you find the slow one, you can use molecularity to knock out the rate law expression. As long as there's not an intermediate, which there isn't. H2 and ICl, they're real. Okay, you're done. Okay. So it's that simple for that type of problem. 2 elementary steps. One is slow, one is fast. The slow one, since it's an elementary step, we can use molecularity to come up with the reaction orders of the 2 reactants. And voila, you're done. I wish they were all that easy. Okay, so I like this diagram. Okay. So energy diagrams for something that has 2 elements, for each elementary step, you're actually going to have a hump. Each elementary step, you're going to have a hump. Okay, this is the first elementary step. This is the second elementary step. Reactants to products. Intermediates, kind of in between. Okay, of course, we have an enthalpy change associated with the first elementary step. It would be right there. That's your delta H. And we have an enthalpy change for the second elementary step. It's right there. And then we have a couple of activation energies. Oh, I guess not, before we do that. We have the overall enthalpy of the reaction, right there. And there's the activation energy. I like activation energies. And this little one right here is the activation energy right here. This one is similar to the one that you saw just drawn just a minute ago, but it adds the transition states at the top of the energy barrier right there. Transition state. Cool. All right. Let's do another one. In this one, it's going to be 2 steps, 2 elementary steps again. The first one's going to be slow, and the second one's going to be fast. Okay. So in this one, this is a good example of, okay, so we have 2 reactants, NO2 and CO, and this actually is what the overall reaction of interest, this is the rate law expression for the overall reaction of interest. Notice it's zero order with regard to CO, so that's why actually you don't see it appear here in the reduced rate law expression. So it's second order with regard to NO2, so right off the bat you're like, ugh, drat. I know it doesn't occur in just one step. If it occurred in one step, then it would be what? NO2 raised to the first power, CO raised to the first power. That's okay. All right. So let's look at possible mechanism. Oh, my thing. I hope that's not a sign. All right. So the way this sort of problem works is oftentimes in homework and or on the test is I will give you a proposed mechanism and you have to prove that it's right or wrong. So first step, slow. Okay, so actually that makes sense because we can use molecularity. That would work, wouldn't it? But, and actually you have homework like this, we need to come up with a second step that basically gets us to our overall reaction of interest. It's kind of like working backwards sometimes. And you wouldn't have to do this, but in your homework, okay, you have to do a little bit of this. But prove to yourself if you want to that if we draw a line here and collect terms and let things cancel, it looks like we have an intermediate, again, NO3. But it looks like things are going to fall into place. Notice one of these NO2s cancel. I like adding equations. I think they're kind of pretty. So when you let things cancel that are going to cancel and you collect terms, you do indeed get your overall reaction of interest, which is definitely an important check, that this could be a practical mechanism. So if this is equal to your overall reaction of interest, which it is, and if the slow step, if you use molecularity and get the observed rate law expression, you're in, okay, which is the case. So that works. So the first elementary step, it was identified as slow. We can use molecularity to write a rate law expression. And my answer keys and stuff, I think to be cleaner, you know, I really think you probably should say the rate 1, and to me, that subscript 1 means that you're getting it from an elementary step. Rate of the first elementary step is equal to the rate law constant for that elementary step times NO2 raised to the second power, because the coefficient from the NO2 is 2. And then down here, then, you can say, you can make the leap that, I don't know, it's a little bit semantics, that the rate is equal to K times the molar concentration of NO2 raised to its reaction order 2, where K is approximately equal to K1. That's kind of semantics. I'll show you another example where I do that, use that convention. All right, I wish they were all that easy. Okay, here we go. So let's do another one. Again, we're going to have 2 steps. The first step is fast this time, and the second step is slow, so we're going to focus on the second step. But we're going to see that the second step introduces an intermediate. And it just makes me so disappointed. So the reaction of interest is this one. Remember that termolecular, not an option. So it's not going to be its own elementary step. But you might be tempted to think that you might be tempted to think that it just happens in one elementary step. You use molecularity of the overall reaction of interest, and you get the observed rate law expression. You're like, dude, well, coefficient of NO is 2, coefficient of BR2 is 1, okay, but not likely. And for this class, no. Okay. So why is it not likely that the reaction occurred by a single step mechanism? Molecular are not likely for this class especially. So molecular equals unlikely. All right. So, like I said, then you'll probably be given the proposed mechanism, and we need to prove that it's right or wrong, but hopefully right. So the first elementary step is fast. The second elementary step is slow. Okay. If we add these two together in combined terms, you are going to get your 2NO plus Br2 goes to form. See, if you're like me, I find myself, and you just got to keep your wits about you, like NOBr is not the same thing as NOBr2. Like, it drives me crazy. NOBr2 is an intermediate. Okay, so actually it's going to be 2NO plus Br2 goes to form 2NOBr. They look so similar. Okay, all right. So what we've been talking about, and I'll go ahead and I guess I can do one more. So what we've been talking about is basically looking at this one, okay, and writing a rate law expression. And we're going to go ahead and do that. But we're going to see that our rate law expression is going to have NOBr2 in it. So it's going to be NOBr2 raised to the first power times NO raised to the first power times K is equal to rate. Okay? That's not going to work for us. So again, probably my convention will be, I probably would put a rate 2 here just to remind myself that this is the second elementary step. I'm turning my attention to that because it's the slow one. I use molecularity to knock out the rate law expression. Okay, but I can't stop because I have to fix this. I call it fix it. Fix this. We can do that. If you're stuck with this, you can usually turn your attention to the thing before it, which is an actually fast equilibrium. I'll show you how to do that. So we're going to fix it by looking at the first elementary step. That first elementary step was fast to equilibrium, and I'll show you how we basically get the molar concentration of that intermediate in terms of things that we can sink our teeth into. This is just, I say algebra, but it's kind of a basic concept of an equilibrium and algebra. I'll show you what I mean. So the first elementary step looks like this. Okay, and we'll be talking more about chemical equilibria, but that definitely goes from left to right, and it has the rate law constant K1, and it goes from right back to left again in what we call the reverse direction, and that has the rate law constant K -1. And those rates are equal. That's the definition of equilibrium. So we can actually come up with a rate law, since it's an elementary step, we can come up with a rate law expression for both in the forward and the reverse direction, and that's what I do here. So in the forward direction, we use molecularity of NO and Br2, okay? And in the reverse direction, we use molecularity of that intermediate, NO-Br2. So rate in the reverse direction is equal to K -1 times the molar concentration of NO-Br2, which is your intermediate raised to the first power. And remember what the blue says. The blue says that these are equal. So now the next thing is basically to take those two quantities and set them equal. If we set those two quantities equal, we are just a hop, jump, and a skip away from getting something that we can fix, we can use to fix our problem. So our problem child is right there. That is our problem child. So that's what we're going to isolate by itself. We can do that. All we got to do basically is move that K -1 over to the other side. And that's what you're going to see here. So our intermediate, the molar concentration of our intermediate, okay, based upon the fast to equilibrium elementary step above our slow step, is equal to the rate law constant K divided by the rate law K1 divided by the rate law constant K -1 times our real things, the molar concentration of NO plus the molar concentration of Br2. So now, I don't know if you recognize a few steps ago, this was what we got from our slow step. So now we are ready to fix, basically we're going to take this quantity and we're going to substitute it in right there. That one's going to go away and we're going to put that in there instead. So here we go. So when we put that mess in for our intermediate, okay, we end up with, again, based upon the rate determining step, the slow one, the rate, I guess I could say rate 2. Maybe, I'm not sure if I want to keep doing rate 2 now or not. We're going to kind of combine our rate log constants. So we bring along our K2, and then we tag along our K1 over K minus 1. And then we tag along our NO, and then we bring down another NO and a BR2. So of course we can combine the NO terms, and we can go ahead and kind of bundle those Ks, and it looks like this. So based upon your slow rate determining step, rate is equal to K, and you can kind of see where the K is actually kind of expanded out into K2 times K1 divided by K minus 1, but K is fine, times the molar concentration of NO raised to the second power times the molar concentration of BR2 raised to the first power. So if you go back a few slides ago, this is actually the observed rate law expression. So not only do the elementary steps add up to be equal to the reaction of interest, but also we can derive the rate law expression, the observed rate law expression, understanding what the slow step is. So smiley faces all around. Alrighty. So let's take a look at what will be due on Monday. These were from last year. I always like it for they're from last year. I'm like, oh, that's nice. Oh, but I didn't mark them. But I think I can find them. Part 6. U2 part 6. 67. All right then. Okay. So yeah, these might be helpful. I'll push these out there again. So I think it's challenging sometimes to take a paragraph and to unwrap it, to put it into a chemical equation, but that's exactly kind of what you're going to do. It says that that first thing is the overall reaction of interest. It says it's second order in NO, so I went ahead and blue wrote second order in NO and first order in H2. 3 steps. The first step is fast. First fast step. Oh, I went ahead and in my hints, I looked up the equation 1425 for you. So there's the reaction of interest, 3 elementary steps. Okay, if you look up 14.25, you'll get that thing that's kind of typed there. It tells you what the last fast step is. The second step is slow. And so the second step actually is what's driving your observed rate. So you need to find something, and it's not termolecular, okay? You need to find something there that will do the trick. See what other hints I have. Okay, and I guess my other hint was, notice that in the first step you get an intermediate formed, so that one has to go away. So it is kind of like playing Sudoku. Somebody said that recently?
So what you're trying to do then is just come up with the second step?
Mm-hmm. Yep. And the second step is going to have an intermediate as a reactant. So the second step, you're going to have to kind of think backwards, that problem we just did, and you're going to have to use the step before it, which is fast equilibrium. Okay? And that's where your actually second order NO is going to help. So you can do it. So two things. Yep, it needs to fit the bill here. It needs to fit the bill here to add together to get the reaction of interest. And when you do the, and I think I have it, one more hint here. For all of mine, I say, after you come up with this, which is great, which is cool, pat yourself on the back. After you come up with this, then you need to go through the exercise we've done a few times in class just now and say, based upon that, can I do the math to come back using molecularity to get this observed rate law expression? So that's what's in red. After coming up with second step, prove it's right. Perfect. Okay, and they're all kind of similar. This one, reaction of interest. Fast reversible. A lot of times this thing on the product side of the equilibrium is an intermediate. This would go down here, and then again, you're supposed to come up with that. What in there would give you the right species, and also then, oh, one more thing. Down the last sentence this time, it said that the observed rate law expression is first order H2 and first order I2. So then I say, don't forget to prove your mechanism, like examples in class. Smiley face. All right, this one, reaction of interest is the top one. They give the observed rate law expression, second order NO, first order Cl2. This one, that says the first, I went ahead and blue, it says it's fast equilibrium. This one, I think you get to even be more creative in coming up with those. But you need to come up with 2 elementary steps that add up to the reaction of interest, and also they shake out, and using the slow step, backtrack to being consistent with the observed rate law expression. Now, this one, I'll kind of leave it up to you. Try this one. If you get the first 3 and you don't get this one, you'll get full credit. Let's put it this way. If you get this last one, because I don't like this last one for some reason. It's not just the typo. If you get this last one, you can have 10 points extra credit. Good for your homework. So, anyway. So, this one actually does have a typo. It says rate is equal to K is equal to, and actually that second equals should not be there. That's a typo. So it should just be K is equal to the second order, rate is equal to K, second order O3, which is ozone, first order O2. Let's see what hints I have. Reaction of interest is given above. So it's 2 steps. The first is fast equilibrium reversible, and the second one is the rate determining one. And that's all I have for my hints. So, okay, it's not that bad, but I just don't like it. So the first 2 are the easier ones. The third one is more creative and complex. Isn't that funny? So, and that's all I have. And so we'll pick up catalysts on Monday, and then we'll go on and do part 7 is really short. And then I do have like a review kind of packet, so we'll kind of take a look at those. That's some kind of review questions we'll do on Monday.